Yeah, hi everyone. So in this hopefully short video, I want to talk about managing common sources of randomness when training deep neural networks. And in fact, I will go over 6 sources of randomness that we might encounter and how to mitigate them. So for instance, assume you trained a neural network like shown here, where we are training it for 5 epochs, and we are showing here the loss during the training and then the final test set accuracy. So you probably all encountered this in practice if you rerun the same code, let's say the same notebook or the same script, that you, even though you use the exact same code, that you get different results. So for example, even though I'm reinitializing the network here from scratch, you can see the loss here and the loss here behaves differently. And you can also see that the final test set accuracy is slightly different. So here it gets 9,809 examples classified correctly, whereas here it gets 9,797 classified correctly. So what has happened here? Why might we get different results when we run the same code again? So one of the reasons is due to model weight initialization. So for instance, here I'm showing a plot where we have the loss, the training loss on the y-axis, and one of the weights of the network on the x-axis. So this is basically the loss versus the values of the weight, how it changes during training. And yeah, in fact, a neural network usually has thousands, millions, and with LLMs, even billions of parameters. And I'm only showing one weight parameter here so that we can initialize or visualize this in a one-dimensional plot. So when we initialize a neural network, we start with small random weights, and they might end up here, let's say, on the loss surface. It's just an example, suppose, where we have an initial weight that is over here when we start training the network, and then during training it converges to usually a local minimum, some loss minimum. And when we reinitialize the network, because it's done with small random values, I actually have also a lecture on why it's small random values and not, let's say, all zeros. But sticking to the topic here, when we reinitialize the neural network, then it might have different initial random values, random weights values, and then it might start, let's say, over here. And then during training, we might converge to a different loss minimum, for example, this one over here. Yeah, so to illustrate that with a small example, suppose we have a small neural network that only consists of one layer, and it has 2 input nodes and 3 output nodes. So the resulting weight tensor has 6 values, 2 by 3, or actually here 3 by 2 because PyTorch always stores the transpose of the weights. So, but the weights here, you can see the tensor is as follows. And if I do the same thing again using exactly the same code, I will actually get different initial weights, as you can see here. So, and this is one of the reasons I talked about, that we might get different results during training because, yeah, the initial weights are different. So we are starting at a different position, and then consequently we might end up at a different end position. So in order to address this, to mitigate this, what we can do is, if we want to get reproducible results, we can set manually a random seed. So which number you choose here doesn't really matter, as long as you choose a number that you reuse when you run the code again, because then, yeah, you can guarantee, like you can see here, that you get exactly the same results. I should note though, in some cases, there are also things like bad random seeds for certain networks. So for instance, sometimes a certain random seed results in a certain initial weight configuration that makes it really hard for the network to learn. So it is actually not a bad idea sometimes to also change the random seed or use a random weight initialization without a random seed if you, let's say, really struggle with the network to get good results. But if you want to have reproducible results, what's important is that you use the same random seed that you used before, so you can actually reproduce the results. For example, that's very important for many scientific research domains. All right, let's now get to point 2, dataset sampling and shuffling, which also affects the training loss behavior during training and then consequently the final test set accuracy. So one simple scenario is also where we have to pay attention is when we are dividing a data set into a training and a test data set. So here that's also where the random seed matters, because that determines when we split a data set into training and test set, which examples end up in the training set and which examples end up in the test set. So that would be one aspect where a random seed matters. Another one is really the order in which the network sees the training data. So for instance, I'm showing you an excerpt from the MNIST dataset here, where I have 2 batches from MNIST, and you can see each batch contains different training examples. And usually what we do is we shuffle the data before training. So there's a specific, let's say, there's a random order in which the network sees these examples. But then if I reinitialize my training order, I run the same script again, what I might have is that this order is different. So for example, here in batch 1, I have 0, 8, 8, 7, 6, and 4. And if I, let's say, repeat this procedure, I might have different training examples in the first batch, like 2, 4, 1, 8, 3, and 5. So yeah, to demonstrate that with a short example, here's a data loader from PyTorch, where I'm having a batch size of 8, and I'm enabling the shuffling here, and then I'm iterating over the whole training set. I'm only printing the last batch, the labels of the last batch here, just for simplicity. So here I have the labels 762538886, and then if I use the same code, exact same code, repeat this procedure, so I'm reinitializing my training loader, repeat this procedure, I might end up with a different set of training labels here. So in this case, we can see, due to randomness, we might change the order in which the network sees the results. So it doesn't really matter for the network in which order the samples are contained within that batch, because during backpropagation we would compute the average loss over that batch. But what matters is in which order the batches then are presented, what data points end up in which batch, because there's one weight update after each batch. So each batch determines how the data set updates the network. So it is kind of important to make sure, if we want to have reproducible behavior, that the network sees the same batches across, let's say, repeating the experiment. So in order to address this, to mitigate this source of randomness, we can, as before, use a random seed. So we can say torch manual seed here, choose our favorite random seed number. I'm very uncreative, so it's just 1, 2, 3. And then if I use the same code again, you might also see that we will get exactly the same batch here as the last batch. So this is another source of randomness. If you want to reproduce experiments, using a random seed also for the data loader is something to make sure you have. A third source of randomness is the use of non-deterministic algorithms. So if you're familiar with Dropout, that would be one example of a non-deterministic algorithm. In Dropout, we randomly drop out nodes in the hidden layers of a neural network. So for example, in one forward pass, we might drop out the second and the third hidden node, and in another forward pass, we might drop out the second and the fourth hidden node. So in this would result in different outputs because different weights will be used to determine or compute these values at the output layers. So to demonstrate that, for instance, suppose we have a neural network with a dropout layer here, shown here, where we have a dropout probability of 50%, which means we're dropping out 50% of the nodes during training. So I'm initializing my network here with using my dropout in the hidden layer. And then when we use dropout during training, for example, we get the outputs. So we don't have to do anything explicitly. We have our inputs. We pass the inputs to the model here. But then if I do another forward pass, even if I use the same inputs, I would get slightly different results, as I can demonstrate here. So using exactly the same input as before, without changing the input, you can see that the model gives me now different results. And that is because of dropout, because it drops out different nodes during training in each forward pass. If I want to deactivate this behavior, for example, one way would be using .eval, which puts the model into evaluation mode. And that is very important when you use the network during inference, because during inference, we don't want to use, let's say, dropout. So in this case, we can put the model into eval mode. Then we call model on X, and now all the nodes will be active. And you can see that if you use the model on the same input, you will get exactly the same outputs. So using .eval, we can then deactivate dropout. And also one more aspect is if you use dropout during training, you want this random behavior. If you use a random seed, dropout will also have the same dropout sequence. So during the first, second, third batch and so forth, it will drop out the same nodes if you would repeat that experiment. So using a random seed is also important during training if you want to get deterministic behavior during training, if you want to repeat the results. But also during inference with dropout, it's important to put the model into evaluation mode. For simplicity, I did not use no grad or inference mode on the previous slide just to keep it simple, but also if you use a model during inference, I highly recommend using with torch inference mode or with torch no grad, because that will disable the gradient tracking. If I go back, for example, you can see it is tracking the gradients, which can be very memory intensive if you use your model in inference. So you're just wasting computation here. So another good practice is also to use the torch inference mode. However, note that this torch inference mode will not make the dropout algorithm deterministic. It will just make the model more efficient by not tracking the gradients. Yeah, now we are already on to the fourth source of randomness, using different runtime algorithms. So you're probably familiar with convolutional networks. But I'm not sure if you know that there are different ways that you can implement convolutions. So I won't go over them in detail, but there are at least 3 methods I can think of. There's the classic direct discrete convolution that is usually covered in textbooks and introductory deep learning classes. But there are also fast Fourier transform based convolutions and Winograd based convolutions based on the Winograd algorithm. So I won't go over those in detail because that would be a very big lecture in itself. I just wanted to highlight that there are different ways we can do convolution, and they typically result all in the same outputs. However, they are computing the convolution slightly differently with different approximations to make it faster on certain hardware. So there are sometimes slight rounding differences due to numerical rounding. And now if we use something like PyTorch, train our network in PyTorch, and then do that on the GPU, NVIDIA is, so usually when you train PyTorch networks on the GPU, you might use NVIDIA graphics cards, and NVIDIA graphics cards they use for that CUDA and cuDNN, which are the libraries for computation on graphics cards, and cuDNN is the deep neural network version for that. And if depending on what type of GPU you have and what type of computer you have, during runtime cuDNN will determine the best algorithm for your hardware based on efficiency on the fly. And I actually talked to NVIDIA employees about that. It's actually a desired, so that's by design, because they want the algorithm run as fast as possible for benchmarks and in general. So there is actually a non-deterministic behavior because these algorithms will be chosen, so the convolution algorithm will be chosen and sometimes even changed during runtime. So depending on what computer you use, you would get different results when you run the same code, which can be a bit annoying, but I guess it's all to make things more efficient. So yeah, there are at least here, top of my head, 3 different ways we can implement convolution. And if you don't want that, for example, when you use PyTorch, you can actually set torch.use deterministic algorithms equals to true, and then it will disable that behavior that the algorithm is determined during, let's say, runtime. So it is not possible for all types of settings. So there are some algorithms that are only available in the non-deterministic version on CUDA graphics cards. But if you want to use or have guaranteed deterministic behavior on GPUs, that is one setting you can try. Otherwise, sometimes the only solution is running on the CPU. Which brings us to the 5th topic, hardware and drivers. So I actually found this snippet in the NVIDIA documentation that says across different architectures, no cuDNN routines guarantee bitwise reproducibility. For example, there is no guarantee of bitwise reproducibility when comparing the same routine run on NVIDIA Volta and NVIDIA Turing and Ampere architecture. So even, let's say, going back, even if you sometimes set everything correctly, use deterministic algorithms, if you run on the GPU, you might still find, due to hardware and driver differences, that you might get different results. So in that case, I guess the only true way to guarantee deterministic behavior is really to run things on the CPU. But the good news is, this is usually only across different architectures. So if you yourself just want to run, let's say, the same code you run today, next week, you should still get the same results. So, and it's more about, let's say, transferring your code to different computers and having different researchers run your code. So on to the sixth point of randomness and generative AI. So I guess most of you use LLMs, ChatGPT and so forth. So I thought that might be an interesting topic. So here on the left-hand side, I'm asking ChatGPT to write a haiku that starts with the word Sunday, because I'm recording this on a Sunday and I'm not very creative. So you can see it comes up with a haiku that says, "Sunday's quiet dawn, leaves whisper in the soft light, peace before the storm." And on the right-hand side, I'm asking it, again, exactly the same thing. Write a haiku that starts with the word Sunday, and you can see now the result is different. So why is that? The reason, there could be many reasons, but one of the reasons is the decoding algorithm. So usually when we use an LLM during inference, we use a decoding algorithm like top K sampling, top P sampling, nucleus sampling, beam search, and so forth. And to illustrate what that means, just focusing on one of them, top K sampling. So for instance, suppose on the left-hand side, we have a prompt inputs. I went for A. So this is a prompt, let's say, for an LLM, and the LLM usually generates the next word, trying to complete the prompt. So when I generate I went for A, it would generate the next token. And the next token inside the LLM, that's not what we see, but usually inside the LLM is a probability over the whole vocabulary. So if I have a small vocabulary with, let's see, 1, 2, 3, 4, 5, 6, 7, 8 words. So I have a vocabulary of 8 words. I get different next token probabilities. So the probability for the next token. Now I could use a deterministic setting where it always selects the next token with the highest probability, and that is also known as greedy decoding. So then the next token would be I went for a run. However, in practice, to avoid, let's say, that the network always generates the same outputs and even memorizes the training set during inferences too much, usually we use something called top K sampling. So top K sampling will select the top, let's say, 3 words or top 5 words, and in this case 3 words in my visualization, and then renormalize those, so the probabilities, so that they sum up to 1 again. It's maybe not the best visualization to show that they are summing up to 1, but I think you get the point. So we are renormalizing those. So now we have these top 3 tokens, and then we would have a multinomial sampling where we randomly select one of those top 3 ones and then use that as the next token. So for example, randomly it could be I went for a walk, and then if I run the network again, it could be I went for a run, or it could be I went for a stroll. But by selecting only the top tokens here before we apply the random sampling, we can avoid weird responses, because if we would sample over the whole vocabulary, we could, for example, get responses like I went for a bike, I went for a fun, which doesn't really grammatically make sense. So it's usually a good idea to only focus on the top outputs. So to illustrate that also with an example, here is a small network that I coded myself. So I'm not showing you the whole code. That would be another book. That's the build an LLM from scratch book, but just to show you some code here. So here I have a function to generate text. I set top K sampling to 3, and you can see based on a prompt every effort it will create the response, every effort has been made to ensure the accuracy of the data and the accuracy of the, it's a bit repetitive, but yeah, it is generating a prompt here. It's not well trained, but the point is really that it generates something, and if I run the same code again, it will result in a different response. Now it says every effort was made to get this to the right place. We have a lot of work to do, but we blah, 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 blah. So you can see running the exact same code results in different output texts. If I want to have random behavior here, if I want to have deterministic behavior, what I can do is I can set a random seed for the initial prompt generation, and then also the same random seed for the second turn here. So setting manual seed 1, 2, 3, 1, 2, 3, I can see now that the network generates the same outputs here. So the exactly same outputs. Another way we can achieve deterministic behavior is the greedy decoding that I mentioned before, and that is by just disabling top k, for example, by only always selecting the top probability token in the vocabulary. So in this case, I can also make sure I get deterministic behavior even if I don't use a fixed random seed. Okay, just to recap, so we discussed 6 sources of randomness in this short video, and I hope you found it useful. So one source of randomness would be the model weight initialization, setting a random seed to make sure that we start with the same initial weights. The other one would be dataset sampling and shuffling, using a random seed when splitting the dataset, and then also when initializing the data loader. Third one was non-deterministic algorithms, to make sure that we use the evaluation mode for the model when we're doing inference, because that will disable non-deterministic algorithms such as dropout. Then there are also different runtime algorithms. For example, we discussed that there are different ways to implement convolution. And in PyTorch, there's a setting, torch use deterministic algorithms, that we can set to true if we want to force it to use always the same, let's say, algorithm, or use a deterministic algorithm when we are training PyTorch models on the GPU. So there was another point related to GPUs, and that is hardware and drivers like GPU architectures. Unfortunately, there is no solution if you're using different NVIDIA architectures, GPU architectures, to make it or to guarantee reproducibility. So here really the workaround would be using the same type of GPU, the same driver version, or just running things on the CPU, which would be, of course, not always feasible. The 6th source of randomness was generative AI and sampling, for example, sampling the outputs. I hope you found this video useful, and actually I also have a little surprise here. I have a new book. It's called Machine Learning Q and AI, where I'm covering 30 more intermediate to advanced machine learning and AI topics. And in fact, actually this video was based on chapter 10, sources of randomness. So if you are interested in 29 more topics that are slightly more intermediate to advanced compared to, let's say, beginner resources, I would really appreciate it if you could check out my book. But I already hope that this video was useful to you, and I guess I see you then next time.